here we are. So sorry I didn't send out the topic for the quiz until yesterday. I just like completely forgot we were having a quiz, but hopefully you guys were able to prepare for it. At least we've been doing determinants and they were on the problem session, so I felt it was fair enough to do that. But let's get started. So I have to get this thing connected, but let's see. There we go. Okay. Okay, so today we are talking about abstract vector spaces, so meaning just like general vector spaces, different than Rn, which we've been focusing on, right? So 4.1, this isn't the actual title of this section, but I think it makes sense to do this, to call this. So abstract vector spaces and subspaces, right? Okay, and basically we are going to use all of the properties that we figured out were true in Rn, and we're going to take them all together and use those to define an abstract vector space. So basically we're saying that it will be a set which satisfies the same properties that we have on Rn, right? So for our definition, this will be so a vector space. We usually use a capital V. If we're talking about, say, two vector spaces, we use like capital V and W. So those are the standard notation for these. So vector space is a set. So this set is consisting of vectors, right? So we'll refer to those as vectors on which we have addition and scalar multiplication. So on which addition and scalar multiplication are defined. Oops. Defined. There we go. Okay. And so not only that, we have the following properties. So just label them. So starting off, if we have two vectors u and v that are in our set V, then when we do the addition u plus v, however that might be defined, that result is in V as well. Okay. We also have that it doesn't matter which order we sum the vectors in, so we can take u plus v, and that is equal to v plus u, right? And we have associativity, which means that we can take u plus v, add those together, and then add w, and that would be the same as first taking v plus w and adding it to u. Okay. There we go. Okay. For number 4, we have some vector that is the 0 vector in the sense that, so there exists a 0 vector, which will still denote 0 in our set V, meaning that V plus 0 is equal to V for every vector in V. So it behaves like the 0 vector. This is capital V. Sorry. Here. This is capital V. Okay. And then moving on to properties having to do with scalar multiplication. If we multiply by a scalar, so we take C times U for some U and V, then, or let me put it this way. If U is in V and C is just a real number, then C times U is in V. Okay. We also have the other properties of scalar multiplication that we had before. So we can do, we can distribute the scalar in this way. We have that C plus D times U is equal to C times U plus D times U, where C and D are both scalars. And we have that multiplying by a scalar, well, 2 scalars is the same as multiplying this 2 scalars together and then multiplying that by, or multiplying the vector by that. And then we also have that multiplying by 1 is, let's see, how do I do?
IX, I think.
Yeah, I just never get this far. So that was a strange moment. Okay. 1 times U. So the scalar 1 times U does not change the vector. So that's equal to U. Wait, did I get everything? That's...
Do we need inverses?
I'm missing something. Yeah, so this is the scalar multiple of U. No, that part we got. Okay, it's that for every U, we can find there exists a V such that U plus V is equal to 0. So it has an additive inverse, right? And so in particular, this V will be just negative U, so negative 1 times U. Okay, that was supposed to go earlier, but I skipped over it. Okay, so this is a pretty long definition, but so for the most part, we won't be checking. I mean, we won't be actually checking every single condition, but we're going to go through several examples. Checking the conditions would be pretty straightforward and honestly just like way too tedious. So you can do it yourself if you want, like if you won't want to do that. Yeah. Okay, so let's talk about some interesting examples of vector spaces, right? So first of all, we have the space of polynomials. So we'll denote this P to the N, and this will be the space of polynomials of degree less than or equal to n. Let me put this here. Okay. I believe that this is slightly different than the definition given in the textbook for this example, because they say polynomials like strictly of degree n, but I think that's kind of non-standard. Like this is more of the space that you'll see more often. So I'm gonna go with this. Might be slightly different than the textbook, but it is, if we want to write this down as a set, this is the set of all polynomials, which look like an t to the n plus, well, all the way down to, so a2 times t squared, a1 times t plus a naught. So our coefficients are these a's, right? And here the ai's are real numbers, and they could be 0.
Could you also write it in reverse order, like from A0 to AN? Like when you're taking your first, I don't know, your first algebra or whichever class, and it's like,
oh, they always write it
1 plus x plus x2. X2, why did I say that? X squared. I'm good at math, I promise.
Yeah, you're fine. Okay, yeah. Yeah, we can write it in the other order if you prefer that. That's totally fine. Okay, so I won't rewrite this, but the definition of addition is pretty straightforward. So if we have two polynomials, p of t, which we'll write in this order this time, and q of t, which has coefficients b0, b1, up to bn, then summing these two things together, so p plus q of t is just a matter of summing those two functions, right? So this is basically what you would think it would be, right? So we get a naught plus b naught plus a1 plus b1. We can actually group these, right? So we get this all the way up to an plus bn t to the n, right? And so when we write it this way, it's pretty clear that this will also be a polynomial in our space. So we do have that property, the first one, right, in our list. Right. Okay. So this is a pretty, I don't know, it makes sense that we would define this in this way, right? We would define the constant times p of t. So multiplication by a scalar would just be multiplying our entire polynomial by c. So we would just distribute it to each term. So you get c times a naught plus c times, c times a1 t up to c times an t to the n. Great. Okay. Right, so this is scalar multiplication. Right here. Okay, so this is our example. We're not going to check any of the other properties, but like I said, it is pretty straightforward to check. Oh, there is one more thing. So the 0 vector here, let me put it this way. This is the 0 polynomial, meaning the one that has all coefficients. Coefficients. Okay, let's just start over. Equal to 0. right? Okay. So, right, and then you can see that if you were to take p of t plus 0, that 0 polynomial, we could even write it like this, you just get p of t back. So that is one of the properties, right? Okay, so this is a good example of an abstract vector space where our vectors are polynomials, so they're actually functions, right? Instead of the like arrows that we've been drawing in R2 and Rn. Another interesting space is the space of 2 by 2 matrices, right? So our set of vectors will be all of the matrices. We'll say they have real values. So A, B, C, and D are in R, right? And then we can just use the definitions of addition and scalar multiplication that we've already defined, right? So we've previously defined addition of matrices. We just add the corresponding entries and scalar multiplication. Okay, 1 second. Okay, how we can create a space without explicitly using vectors, since I'm so used to finding a set with a list of vectors. I mean, yes, it's okay if you feel confused. Yes, I know it's so we're taking like a big step outside of like what we've been doing, right? So that's why I even added the word abstract just to like, you know, emphasize that we're kind of like stepping outside of what we've been doing up to now. But I think it's best to try not to overthink it, right? So we're just saying that we can apply there's a similar structure to these other collections that like mimics Rn. Maybe that's how to think of it. Yeah. Okay. Right. So we have these 2 by 2 matrices. We have already defined addition and scalar multiplication. So we'll just use those as our two operations. And the 0 vector in this case is just the 0 matrix. Right, so the one with 0, 0, 0, 0, right? Okay, so this is another interesting example. We can also look at the set of all continuous functions. So this would be, say we'll look at the set of all continuous functions whose domain is the interval a to b and whose codomain is R. So just all of the collection of functions like this. So we have a particular notation that we use for this. We use C, so it's a script C, and so C stands for continuous, right? And then we put the domain in parentheses, right? So this is the set of functions from A, B to R such that F is continuous. Right? Okay. And then we essentially, our addition and scalar multiplication is the same as what we used for polynomials. So just because adding two functions together has a pretty straightforward definition or a natural definition, if you will. So f plus g will just be f of x plus g of x, right? And c, the scalar times f of x, well, that's kind of, you know, well-defined already. So this is our addition and scalar multiplication. So example 1, the space of polynomials, and example 3, the space of continuous functions. These are both called function spaces, right? They're spaces made up of functions. Right, and they do come up in other areas of mathematics. So they are pretty interesting. And the fact that they are vector spaces is often used as well. So that's a really convenient property for these spaces, right?
So what would not be considered not a vector space?
Yeah, so we do have examples. Let's see. In fact, I will do an example later once I define something else. So we'll see that in a bit, right? Okay. Let me, if I can think of one off the top of my head.
The integers, rational numbers.
Right. So there's a lot of things that are like, let's see. Like, okay, so I don't know. If you look at, say, even in R2, do I like this? I don't know. Okay, never mind. Well, okay, I guess it's okay. Okay, so in R2, if you were to take, say, like the X and Y axis, together, I mean, that's a set, right, inside of R2, and it is not a vector space because you could add two vectors sitting in there and you would get something that was not in your space, right? So that's sort of related to this idea of a subspace we were talking about. So, right, so we have that this property that it's not closed under addition. That's one property that it might not satisfy, right? Something that's more abstract is harder to like come up with off the top of my head. Oh wait, sorry. So this question A and B, were you referring to these right here? Like the A and B in this third example? Yeah, okay. So A and B are just real numbers.
Sorry, I guess what I meant is like, where do they go? What do they interact with? Or it's just some black box function that we input them into, and then we get a result that's a real number.
Right, so it is just a black box function. We don't have any more information about it, just that it's continuous and its domain is the interval A to B. We could use, if you want something more concrete, we could change this to functions on the interval 0 to 1, right?
Oh, so it's an interval that the function is continuous on?
Yeah.
Okay.
So this is an interval. Maybe I'll do it. Yeah.
Wait, sorry, an interval or an integral? Okay, sorry.
Interval, yeah. Okay, so.
Also, did we need to finish up the scalar multiplication proof?
For this one here,
Yeah.
I was just going to leave it as that.
Oh, okay, cool. Yeah. Okay, thank you.
So yeah, without like verifying anything, we'll just say that this is a vector space. Yeah. Okay, so we not only have So maybe I'll just finish this up with some words. This is not a vector space. For example, the vector 1, 0, or taking 1, 0 plus 0, 1 equals 1, 1 is not in this set or space. Okay. Okay, and related to vector spaces, we also have the notion of a subspace of an abstract vector space. So this is really just the same definition that we had before, but now we're talking about a set V, and we say that a subspace of a vector space V is a subset. So it has to be contained inside of the space for one. We usually use H for subspace. So this is a subset H of V such that we have the following properties. So first of all, the 0 vector is in H. So V being a vector space, it must have a 0 vector, and this being H being a subspace means that it must contain that 0 vector, right? Okay, secondly, H should be closed under addition. So if we were to take U and V in H, then U plus V is also in H. And if U is in H and C is a real number, then C times U is in H. So it's also closed under scalar multiplication. Okay. So for example, so relating to some of the examples that we already talked about, we talked about the continuous functions on an interval, but we could also define a space that would be continuous functions on the entire real line. Right. This is also a vector space, and it would use the same definition of addition and scalar multiplication, right? Okay, so this is a vector space, and the first example that we looked at, those polynomials of degree n, is a subspace of this vector space. Maybe, okay, let me put this. This is a vector space. And the polynomials of degree less than or equal to n, are a subspace of this vector space, right? Since, well, first of all, it's a subset because polynomials are continuous. So that's the first thing. The 0 vector in this case is just the function that's identically 0, right? So the constant function 0. And oops, we know already that P of n or Pn is closed under addition and scalar multiplication by the fact that it itself is a vector space. Okay, and just to be clear, so this means that Pn is a subset of the continuous functions on R. Okay,
What does the little what's the curly C?
that's the notation we use for continuous functions.
Thanks.
Okay, so there's an important sort of non-example or something to be careful of. So R2 is not a subspace of R3. And that is because they are made up of different objects. They really, the vectors themselves or the things that make up those two spaces are completely different, right? So R2 is made up of vectors with two entries. So it looks like this. So vectors AB, where A and B are real numbers, and R3 is made up of vectors A, B, C, such that A, B, and C are real numbers, right? So we don't have that R2 is a subset of R3. So that is the first requirement for something to be a subspace, right? It actually has to be a subset. It has to be made up of the same types of objects, right? Whereas in our example here, the sort of base object is a function, right? And so polynomials being functions can be a subset of all continuous functions on R, right? Okay.
So with this similar logic, could you say like R3 is not a subspace of R4?
Yeah, exactly. So none of the different Rn's, if you will, are subspaces of each other if the n is not equal, right? I hope that made sense. So maybe, so Rn cannot be a subspace of Rm if n does not equal m. And if it is equal, then they're just the same space, really.
Yeah, but there's still a subspace inside of R3 that is like the same thing as R2, basically, right?
Right, yeah. So if you were to take H to be just the vectors A, B, 0, right? Like this acts like, or looks like, maybe is a better way of putting it, looks like R2 sitting inside R3. And in fact, any plane through the origin sitting inside R3 will be a subspace, right? Maybe I'll know that and is a subspace. Okay. Okay, but we should be careful not to say that H is R2, right? It just is very similar to R2. Okay.
Also, in this case, H is like a set of all vectors and like which basically their third component is 0.
Mhm.
Okay.
Yeah, so it would just be if you're looking at R3 and say this is your x1, x2, x3, right? these are the points with the first two coordinates being, well, any real number in the third coordinate being 0. So sort of this third, it's this plane right here, right?
So it's basically flat in this.
Yeah, exactly. And so, yeah, any other like, okay, I'm not going to try and draw example, but yeah, any other plane through the origin is also a subspace of R3. Right. A plane not through the origin, so maybe I'll also add that too. A plane that does not pass through the origin is not a subspace because it won't contain the 0 vector, the origin. Okay. Okay. And so we have a nice little fact that is not too hard to verify, so I won't go through that, but if you have some vectors v1 up to vk in a vector space V, then if you take H to be the span of V1 up to VK, then this is a subspace of V. Okay. And
This, oh, sorry.
yeah, go ahead.
The V with like the little lines on top, is that just a fancy way of denoting a vector space?
Yeah, I'm just trying to make it look different than my lowercase v's, so it's not confusing.
Cool. Okay, I
It's
like it.
supposed to be a capital V, yeah.
It looks fancy.
Okay, cool. Yeah, so this fact, like I said, it's not too hard to check. So to verify this, you just want to check those 3 conditions that tell you that H is a subspace. So you just want to check that 0 is in H, and that if U and V are in H and C is a constant, a real number, then where should we put and? Then you have both U plus V is in H and C times U is in H. Right? So, right. Okay, and just note that the span in this case is defined in exactly the same way as how we defined span earlier. So a lot of the definitions that we've already given are going to apply directly to abstract vector spaces as well, right? So including linear independence and dependence and this span and some other things as well. And the notion of a basis, like several things. Okay, so we can have a somewhat interesting example of subspace, but first we should define something which is called the trace. Okay. So this is a trace of a matrix, right? Okay, so like the determinant, this is just a number that you compute that is given for any matrix, any n by n matrix, that is. So if you have an n by n matrix, is an n by n matrix, then the trace of A is, well, first, this is denoted TR of A is the sum of the diagonal entries. Okay, so it's actually a lot easier than the determinant to compute, right? We just take a look at our matrix and take the sum of the diagonal entries. So if we had a matrix A like this, the trace of this is just the sum of the diagonal entries, right? So it is 1 plus 5 plus 9. So 15. Okay. So one property of the trace is that if you take two matrices and add them together, so if we have two matrices A plus B, both n by n, and we add them together, then this is equal to the trace of A plus the trace of B, right? And so,
Intuitive sense, because when you're adding,
yeah, exactly. Like if you imagine just adding those two vectors together, you know that you will add each of the diagonal entries together, right? So yeah, that's exactly what's going on here. So we can look at just some 2 by 2 matrices, and we can see this going on. So we'll use B11, B12, B21, B22. When we add these together, we of course get A11 plus B11, 12 plus B12, A21 plus B21. And then you can see that the trace of this guy would be, I don't really want to write this out, but yeah, then you can see that trace of A plus trace of B is equal to trace of A plus B. Some other things, so this is one property. Another thing is that the trace of the identity matrix. So this is just ones along the diagonal. There will be n of them if it's an n by n identity matrix. So the trace of the identity matrix of size n is n. And the trace of the zero matrix is just 0.
so trace is only defined for square matrices.
Right, yeah, because sort of that's got like a main diagonal that's like symmetric, right? Yeah. Okay, so we can define, or so we can use this to talk about some spaces, some subspaces. So let's consider, we talked about the space of 2 by 2 matrices, right? But similar, we can define the space of 3 by 3 matrices. with entries in R, right?
Like, could another property of trace be like, if you take the transpose of A, you get the same trace?
Yeah, exactly. Yeah, we can add that to our list as well. Yeah, because when we take the transpose, it does not change the main diagonal. So yeah. Okay, so here we're considering the space of 3 by 3 matrices, and H being a subset of M3. So these will be all 3 by 3 matrices such that the trace of A is equal to 0. This is a subspace. Okay, so we can first think about the fact that the trace of A plus B for 2 matrices whose trace is 0 will just be, like we said, the trace of A plus the trace of B. If both of those are 0, then the trace of the sum is 0, right? Also, if we look at C times, so a scalar times A, the trace of that will be still C times, well, this is another, I guess, property of trace, but yeah, this will be C times the trace of A, and that will also still be 0, right?
Can you walk through again, like what the first line, trace A plus B equals trace A plus trace B equals 0, like what does that specifically prove?
Oh, so this means that, let's go through here. Okay, I'll put more words in here, sorry. So if A and B are in H, then the trace of A equals 0, and so does the trace of B, right? Because that's just the definition of that space or that set, right? Then if we consider A plus B, we want to know, is that in H as well? And the trace of A plus B is the trace of A plus the trace of B. Both of those being 0 means the trace is 0. So this means that A plus B is in H. And then also this means that C times A is in H. So it's closed under addition and scalar multiplication. And it also contains the 0 matrix because the trace of the 0 matrix is 0. So this is a subspace. Okay, but we can define another space. We could call this, I don't know, H tilde, something else, where we take matrices that are 3 by 3 such that the trace of A is equal to 1. This is not a subspace.
I guess because the 0 matrix is not in the in that space.
Exactly, yeah. So there's a few problems. So first of all, the 0 matrix is not in this space H tilde. Also, if A and B are in H, then the trace of A plus B is equal to 1 plus 1, which is 2, which means that this falls outside of the, so A plus B is not in H tilde. And then thirdly, if you multiply by any constant not equal to 1, then C times A is not in H tilde. So there's actually a lot of problems with this space. Yeah. So subspaces are vector spaces in their own right? So if you're thinking of examples of abstract vector spaces, if you think of, or if you're able to construct a subspace, you could see that itself as an abstract vector space, right? So yeah, just like we had the polynomials sitting inside of the continuous functions, we saw that the polynomials themselves were a vector space, but they're also a subspace of a larger vector space. Okay, so you do. Oh, go ahead.
Sorry, could you like theoretically take a vector space and get a subspace of it, and then consider that subspace as a vector space and get a new subspace of that? Like, could you infinitely get subspaces out of?
You could not do that unless you definitely had like an infinite dimensional subspace. Well, I guess. I'm not entirely sure you could get like infinitely many subspaces. Yeah. Maybe if you chose them correctly. Or eventually you'd have like trivial subspaces that are actually just like equal to the one before it. Yeah, so let's see, how are we doing on time? We can do, okay, so, sorry. I think I want to talk about, yeah. Did we talk about span? Yeah, we did. Okay, cool. So there's one more example that we'll do that is related to ODE. So maybe it will be more familiar if you've already taken or are taking ODE, but if you've at least had calculus, this should make sense. So consider the following differential equation. F double prime minus F equals 0, right? So this is a pretty simple differential equation as far as the differential equations go. So if you've not seen any differential equations before, it's just an equation involving the derivatives of a function, right? Just generally. So you can see that this is an equation involving F double prime and F. And you can check that the function e to the x satisfies this because, so satisfies this equation since we can just go ahead and compute f prime equals e to the x and f double prime is also e to the x. So that means that f double prime minus f is e to the x minus e to the x, which is 0 for all x. Right. So it's important that this is satisfied for every value of x, right?
What about e to the negative x? Would that also be a solution?
Yes, e to the negative x is also a solution. And you would learn in ODE, or you could just see by verifying this, that the general solution, so like the most general form of this solution would be, I'll just use this notation, y equals c1 e to the x plus c2 e to the minus x. right? Where C1 and C2 are constants. So notice that this is a linear combination of the two solutions, right? Okay, so in fact, if we look at the space, so the set of all functions that satisfy this differential equation, this is equal to the span of e to the x times e to the minus, and e to the minus x, sorry, not times, right?
Yeah. Okay.
Yeah, because the span is just all linear combinations of those two things,
Yeah.
right? Yeah. So this space right here is called the solution space of this differential equation. Yeah. And so you can see that these, there's a strong connection between these particular differential equations, these linear differential equations, and linear algebra, right? We can express the solutions as a span, which is a subspace, right? Or a vector space in its own right. So e to the x and e to the minus x are solutions in that if we plug them into the equation, they satisfy the equation. So we call them solutions. Yeah. Okay. So, yeah, so I think that a lot of these examples are pretty interesting. It's like cool to see that these ideas transcend this sort of like Euclidean space that we've been working in, right? So we'll talk some more about basis and linear independence and dimension. So, you know, there are infinite dimensional vector spaces. That's really interesting. Yeah, but we will be getting into that in the next few sections. Okay, so I guess I will let you guys, I didn't put the quiz up yet. I will let you guys take the quiz in a second.